Okay, so we are in the tunnel FET. I'm a little bit slow, but I still like that, right? Now let's review the subthreshold slope one more time. What is subthreshold slope? Can someone tell me what is subthreshold slope? That may be our 6th time to review this, and we did it in midterm, right? You should be able to tell me what is subthreshold slope. Really, no one?
It's like the slope to increase the current by like factor of 10. How much voltage?
The amount of voltage, right? You need to increase in order to increase the current by 10 times. For example, from here to here. Let's say this is 1e minus 7. This is 1e minus 6. And then maybe this is 80 millivolt. Then the subthreshold slope is 80 millivolt per decade. But why we have this problem here? Why we have the subthreshold slope? That is just because our transistor is operating using this principle, right? Vg. We have a oxide capacitor here, and then we have a depletion capacitor here. Our goal is to change this phi s. Okay? And in order to change this phi s, we need to go through the capacitor divider, right? This is Cox, this is CD. We say that this is the conduction band, this is D, this is source, and on top of it, you have the gate. And then on the bottom, you have the CD, right? If you are able to move, for example, by increasing the gate voltage by this, because of the Fermi-Dirac distribution, right? You get more electron through it, right? So this might be B point, and this might be the A point, right? So if you're talking about just this fermionic emission, it is just d psi s d log 10 ID. This is basically just how many surface potential you need to change in order to increase 1 decade. And this one gives you natural log KT over Q. But from the Vg, in order to control the psi s here through Vg, you still have this capacitor divider effect, which is 1 plus CD divided by Cox, where we call it 1 plus N. Do you still remember this? Any questions? Now I want to ask you, last time we talked about negative capacitance transistor. We say that we are able to get sub 60 millivolt per decade. How did we do that? Which term did we change? How we were able to make S smaller than 60 millivolt? We have 2 terms. Which one did I change? For negative capacitance FET, NC FET.
The capacitance?
How did we change it?
Made it negative.
We make negative capacitance, right? So that 1 minus 1 plus n is smaller than 1. We change this term. Okay. With negative capacitance, so that 1 plus n smaller than 1. So last time we showed that I can increase the subthreshold, make the subthreshold slope very steep by playing with this term, 1 plus n. This time I'm going to show you, hey, if we don't change this term, how about can we change this term? Is it possible to change this term? It's impossible because this is physics, fermionic emission. Then it means that if I want to change this term, I need to change the conduction mechanism. I cannot rely on fermionic emission anymore. And that's what we are doing for the tunnel FET. Is that okay? I hope that you are okay with this slide. If not, go back to review one more time, right? I understand why we can change the subthreshold slope in the negative capacitance. And now what we're doing is to change the conduction mechanism. Before that, let me just briefly go over the energy crisis, what we really want here, right? This is the IDVG. We want to have a very high I on, I off. It means I want to have I on here, very high, and I off here. So how do I get high I on? It means I need to have large VDD minus VTH, correct? But the problem is to save energy. I want to reduce VDD. I want to reduce VDD. Okay, you reduce VDD, that's great. But if I still want to keep the same amount of, and then to keep VDD minus VT, I need to reduce VTH, right? First, I want to save energy. I need to reduce the VDD. And then, but I want to have high I on. Then I need to keep VDD minus VTH. Means I need to reduce VTH. And that is what happened. This is 1. This is 2. And because of this, what happened? I off increased substantially. What is the solution? The only solution is reduce the subthreshold swing. If I can make it very steep, like this, then I can have high I on, low VDD, and low I off at the same time. Okay, I'm going to cover this on Wednesday. Okay, thank you. We need to know the keyword when you learn something. And the same when you interview or you give a talk or when you talk to your VP. You know everything, but you don't have time to draw all this graph and going back and forth. A few important logic you want to know in your mind to show that you are the expert, right? And that's something like the elevator pitch, right? You saw your VP in the elevator and you only have 1 minute or 30 seconds to express what you have to impress him, right? So that later you might get a promotion because of this or whatever. The main point here is that, wow, we have energy crisis, like not really we don't really be talking about we don't have enough energy in the world or too much CO2. This is a result, but more is about we have to spend, we use too much energy in the chip. right? We use too much energy, so there's heat up, and we cannot scale up the computation. So the main point is that to save energy, we need to reduce the VDD. Why is that? Just because we know power consumption is proportional to the CV square and also the leakage. Right? This is related. This virtually we study quite a lot in EE 224 to be offered in the spring this time, right? And so you see that I need to reduce the voltage. Once I reduce voltage, I reduce the power quite a lot because CV square. But the problem is I reduce the voltage, I need to keep what? VDD minus VT to be the same so that I have a high current, right? Otherwise, if VDD equal VT, I don't have on current, it doesn't work. So if I scale VDD, I need to scale the VTH also, right? And that's why saying that for the same performance, I need to scale the VTH. But look at this, when I try to scale the VDD, the curve will shift to the left if I keep the same VTH. If I have the same subthreshold slope, which is governed by the physics, 60 millivolt per decade at best, then it means my current is going up exponentially. Don't look, remember, this is log current, exponentially, maybe 10,000 times. And that is a big deal. Okay, so what is the solution? Reduce the subthreshold slope, right? So our goal is that, okay, I move my VDD to here, and then I move my VTH to here. I still have the same on current, but let me have a very steep slope, so I still have the same I off. That is perfect. That's what everyone wants, okay? Is this scenario, does it make sense to you? Any questions? Now, let's say you don't have question. Then I will continue just to tell about this energy crisis one more time. I already gave you the equation, but this is a more complicated one. But you don't have to memorize it, okay? You only need to have an idea. I don't expect you to memorize this equation. Total energy consumption is the dynamic one. That what I said earlier, CV square, and also the leakage. I of times VDD. Here is more complicated. It talks about alpha, which is the logic activity. If there's no switching, you're not consuming any dynamic power. It also gives you the logic depth, right? If your logic has many depth, then of course you increase the consumption. It's just saying that you have a train of inverter or NAND gate or whatever, okay? Right, and then they come up with an equation. But after all, the main point is this: you see that the total energy proportional to V square. This is due to the dynamic power. But at the same time, if you keep reducing the VDD, you actually increase the power consumption due to the leakage. This part is the leakage. And why is that? Because it's limited by subthreshold slope, just like what we show here, right? You keep reducing VDD, this part is going to go up. This is one thing, not just this one. Actually, I'm not clear enough. Second thing is your logic is slower. Slower means more time at off state. It also means more leakage overall, right? You just keep your logic in the off state. So a lot of time is leaking current, right? So this is generally what you see. When I increase the VDD, the power will increase a lot. If I reduce the VDD, actually the power will also increase per cycle, right? You can imagine, what if my clock cycle is 0.1 hertz? It takes 10 seconds to do one operation. But within 10 seconds, you need a lot of power, right? Compare with 1 gigahertz, you need 1 nanosecond to do one operation. Within 1 nanosecond, it actually need much less power because it's 1 nanosecond only. But it has a lot of switching power. So there is a balance. What we want to do is to find this optimal point, right? You learn this in the digital circuit. For example, we will mention this in EU224, right? I don't know, maybe other classes also mentioned it. But the point is that you want to get the minimum energy with this VDD. But this all determined by the transistor. If we have a subthreshold swing that is less than KT over Q, then we will have another curve. But the main point is this. This curve is going to shift in this direction. Lower energy with lower power. Okay? Because if you try to change your logic for the same technology, you might not be able to get lower energy, right? For example, I try to reduce the VDD, you might go up the energy, right? So that is the idea, right? Any question about this? I don't require you to understand this equation, but only need to understand higher VDD, you get a lot of power, that makes sense. But lower VDD, actually the energy per cycle also increase. So do not say that, let me just do things extremely slow, right? That is very easy to understand, right? For example, you say, I want to save energy. Let's just do sleep on the bed for 10 days and then do one exercise. But you sleep on the bed for 10 days, that is your leakage energy. You're still consuming energy, although it's low, right? That is just the same concept. Any questions?
Professor? Hello?
Yes.
Professor, I don't exactly understand, like, what do we take from this concept, like energy crisis theory? Is it like, should we just conclude that if we increase the VDD, the power increases, and if we reduce the VDD, there is still increase in power per cycle? So that's the thing that we take from this point?
Yes. So here I try to tell you that there is a minimum point that give you the minimum energy for certain VDD. And if you have a certain technology, it is here. If you can able to go to subthreshold swing, right, less than the thermal swing, then you can get to an even lower point. That is the purpose of this slide.
Okay, Professor.
Do I answer your question?
Yes, Professor.
Okay. Any other questions? Okay, so definitely we see that it's very useful, right, to have a steep slope device, right? Let's take a look again. Assume that we have it, right? Then what happened? The blue one, the red one, I have asked you to draw this in your, I think it's assignment, right? Is the bulk silicon MOSFET. It has this slope, okay? So to have the same on current, if I go to with multi-gate, like FinFET, I can have the same on current, but I have a steeper subthreshold slope that is closer to 60 millivolt per decade. And you see that I have less leakage current. Okay. Now, if I use some high mobility device, we did not really mention too much about this, right? But let's say you have high mobility device like the gallium arsenide, silicon germanium, you increase the on current, right? But still, then at the same time, you will increase the off state leakage just because of the subthreshold slope, right? I also asked you to draw the ideal switch before. It should have very low current and suddenly go up with very high current. So what is a tunnel FET? Tunnel FET is like this, the green one. You see that it has a steeper slope, just like the ideal one, closer to ideal, right? And at the same time, if you look at the region of A, it has a lower leakage current than your regular red one, the bulk MOSFET. And it also has a higher current here, but still in the subthreshold region. The problem of tunnel FET is that it usually has low on current. This is the problem. We cannot do it well at this moment due to its physics. So we can have a very high subthreshold swing, but the on currents usually cannot compare with other devices. However, then it means that, right, this is good for ultra low power application. Or for low VDD, very low VDD, right? In some circuits, we want to make the VDD so low, for example, IoT. If your VDD, for example, the 0.8, if this is the VDD, right? I call it VDD8. Which technology would you choose if my VDD is only VDD8? It's very obvious. I would choose the tunnel. Yes, A, the tunnel FET, because it has higher on current. Although it's subthreshold, but now the highest is called on current, and it's the lowest off current. Of course, I will choose this one. If I choose for example, the bulk MOSFET, it has larger off current. It keeps leaking the current. At the same time, it's smaller on current, right? But if you have technology that require me to have VDD-B, then it's difficult to say. I might choose the multi-gates because they have similar off current. Yeah, there's some difference, but the on current is much different, much higher in the multi-gate case, right? Here we also look at the performance versus the energy consumption. Performance usually is talking about the speed. Let's say your circuit doesn't need a lot of very high speed. For example, let's say a pacemaker, right? My guess is, I don't know about it well, but my guess pacemaker doesn't have to have high speed, right? How fast does your heart beat every minute? Let's talking about maybe 1 hertz, in the order of 1 hertz. I don't need gigahertz or even megahertz of operation. Maybe kilohertz of operation is good enough to make my pacemaker to work well. So when it is in the low performance space, then let me use tunnel FET, because for the same performance, I have much lower energy because I have low leakage and also higher current, right? Then I don't need to change the battery maybe for, let's say, 100 years. That would be perfect, right? Usually no one lives more than 100 years, right? So when you put the pacemaker, just keep it forever, right? No one wants to do surgery to take out the pacemaker. Of course, they can do wireless charging or whatever, but still this is good, right? Same for IoT, right? Put in the wall. Usually the building won't last more than 100 years. Then we don't need to take out the wall. In the future, IoT, we can put IoT in every break in the wall if it's cheap enough. It just keep monitoring. Is it broken? Is it too humid? Any termite? Well, that would be wonderful, right? So that is the niche market for tunnel FET. Although we still try to push for high performance, but this is what it is excelling at this moment. Okay. Any questions? So I hope that you have this picture in your mind, right? When this is just the key point. When people ask you what's the difference, why I care about that. Okay, and this is just a definition of FH subthreshold slope. Never mind too much, I just give you. So let's start. What is the physics?